Calculating molality. So first of all, I know it's confusing, right? So we often use molarity as our unit of concentration in chemistry, which has the symbol capital italic M, and that is defined as moles of solute per volume in terms of liters of our solution. So moles per liter. Easy peasy, right? But as you know, there are multiple ways to define concentration with different units. Like you may have also met parts per million, 1 gram per million grams of solution, right? Parts per billion, 1 gram of solute per billion grams of solution. So there can be multiple different units for concentration. And another one that we need to know for chemistry, particularly for colligative properties, so properties of solution, is molality, which unfortunately is only one letter different to molarity and has the symbol in italic small m. So I'm sorry, them's the breaks. So that is moles of solute, if I could spell solute, per kilogram of solvent. Okay, very similar definition. So what is the point of molality? The point of molality is that the density of a liquid does change somewhat with temperature. So molarity, if you're using it as a definitive unit and you want to compare concentrations across like different temperature range, molarity is not as useful as molality because the mass of solvent is not going to be affected by the temperature unless you're up near its boiling point, right? It starts to boil. But anyway, overthinking things. Okay, so if we have to calculate our molarity and our molality of our methanol solution, well, we are going to definitely need our moles of our solute, which is our methanol. So I guess we should go ahead and calculate that. So my molar mass of methanol, CH3OH, is going to be, let's see, 1 carbon, so 12.011 grams per mole plus 4 total hydrogen, so 4 times 1.0079 grams per mole, and 1 oxygen, so 15.999 grams per mole, and I got that comes to approximately 32-ish, 0416 grams per mole. You may have slightly different depending on how many sig figs is on the periodic table you're using. If you are working in ALEKS, I suggest you use the ALEKS periodic table just to be sure. So then, of course, we can convert mass in grams to number of moles using the molar mass as a conversion factor. I always recommend writing the molar mass as an equivalency. So every 1 mole of methanol weighs exactly 32.0416 grams. Then if I'm converting mass to moles or moles to mass, it doesn't matter. I'm just going to use it whichever way up. I need to make that conversion. So I'm converting grams. So I want my 15 grams to convert to moles of methanol. So I'm going to need grams on the bottom. So that 32.0416 grams goes on the bottom. My 1 mole of methanol goes on the top. And that comes out to moles point 46814 dot 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 moles. That's probably enough sig figs for my purposes. We're only going to go to 2 significant digits, so that is fine. All right, so mass in grams count cancels out, and we got number of moles of methanol. Okay, so molarity should be pretty straightforward. So it's going to be moles of solute over liters of solution. However, we've been given our volume in milliliters, so we've got to remember what our SI unit prefixes means. 1 milliliter is the same as 10 to the power of -3 liters. So there's my equivalency, and I can just stick that straight in as a unit conversion if I want to. Okay, so moles of solute, I had 0.46814 moles. Divide by that volume, which is 325 milliliters, and then I got to convert milliliters to liters. So 1 milliliter, take that equivalency I just wrote and stick it into a unit conversion, 10 to the -3 liters. Bish bash bob, Bob's your uncle, etc. Let's just tidy that up a little bit. So I can see that I'm going to end up with units of moles per liter, which is correct for molarity. And I get zero, no, not zero, 1.4404 moles per liter. I can tidy that up to, let's see, 2 sig figs. So it's just going to be 1.4 moles per liter to 2 sig figs. So my molarity is 1.4 moles per liter, or Italic M, if you prefer. Okay, so what about the molality? I need my kilograms of solvent. So again, I can use the density to work that out. Okay, so density is mass over volume. Oh. Therefore, if I want to get my mass from my density and my volume, I just need to rearrange and solve for my mass is going to be my density times my volume and check that the units cancel out appropriately. We should check that. So that is going to be my density is 0.82 grams per milliliter. Times it by my volume, which is helpfully in milliliters. So that's 325 milliliters. Now that's going to give me my mass in grams. I want mass in kilograms, so I should use the equivalency that 1 kilogram is 10 to the power of 3 grams. So I could just do that all together to get my answer in kilograms. All right, so milliliters cancels, grams cancel, and I end up with my mass in kilograms, which is what I'm going to need to get my molality. Come here, text box. So that is going to come out to be 0.2665 kilograms. So now I can calculate my molality. So molality is going to be molality, my number of moles, which were, what were they? I've got them somewhere. 0.46814 moles. My mass in kilograms of my solvents, 0.2665 kilograms. So that's going to give me my molality in the correct units. And that comes out to be 1.7566 moles per kilogram. I'm going to have to stretch this out a little bit, which is, to two sig figs, 1.8 moles per kilogram. Running out of space again. All right, let's move this out the way. So, that's all you need to know to answer this kind of question. Some of you guys may be like answering these questions and thinking, some of my answers are very similar in molarity and molality. Moles per liter versus moles per kilogram. You're getting a very similar number. Why is that? Well, think about it in terms of your density of a lot of liquids tend to be around about 1 gram per milliliter. That's what it is for water, right? So if you were going to convert grams per milliliter, 1 gram per milliliter, use a little bit of dimensional analysis, right? So 1 milliliter is 10 to the power of minus 3 liters, and then 1 kilogram, where are you? 1 kilogram is 10 to the power of minus 3, sorry, 10 to the power of 3 grams. So let's look at our dimensional analysis real quick, if I can find my little liney drawy thingy. So grams cancels out, milliliters cancels out. So density of 1 gram per milliliter is equivalent to a density of 1 kilogram per liter, right? Same as 1 kilogram per liter. So look at our units of molarity versus molality, moles per liter, moles per kilogram. So when our density is around about 1 gram per milliliter, that is the same as about 1 kilogram per liter. So the number on the bottom for our molality versus molarity is going to be essentially a very similar number if we're near to 1. So that's why you might see a lot of very similar numbers. All right, hopefully that helps and answers some of your questions.